All right, so we're going to be looking at the properties of definite integrals. Okay, so all of these can be proven using the definition of the integral, the limit definition of the integral. So we'll see a lot of these follow from the limit definition or the limit properties that we looked at before. The first one is we have this integral, and if we switch the limits of integration, so instead of going from a to b, we go from b to a of the same function. Well, we're allowed to do this as long as we make the integral negative. Okay. Our second property is if we take an integral from a to a. All right, so essentially, the area under a curve from a to a. Well, that's like having a width of 0 for that rectangle. So that's going to be 0. Okay, the other one is taking the integral from a to b of a constant. Okay, and we can visualize this over here. Let's get the graph of a constant going. And if we're looking at the integral from a to b, whoops. The area under the graph is going to be a rectangle because our graph is a constant, right? And the parts of the rectangle, well, if our constant is like y equals c, then the height of our rectangle is going to be c, and the base is going to be b minus a. And so the area is b minus a times c. So that's what your integral is. Okay. Some other properties. We saw this with the limit law or limit properties as well. If we're taking the integral of a sum or a difference, I'll write it like that. We can take the integral of each function individually and then take, whoops, I forgot the dx, and then take the sum or difference. So that's a direct result of one of our limit properties. Okay. Some other things that come, or another one that comes directly from our limit properties, if we have a constant times a function, guess what we can do to that constant? We can move it outside. All right, and then finally, the last one we're going to look at is if we have the same function and we create a stopping point in the middle of our interval a to b. All right, and then we add them up. Okay, so visually what this looks like on the graph, we could have a function, this be f, from a to b. And what we do is we introduce a number between a and b. And so this first one right here is the area under the curve from a to c. And then this next integral is telling us take the area under the curve from c to b. And guess what happens when you add up those two areas? It's like the area from a to b. Okay, so this is telling us we can break up regions, but when we add the areas together, it's like the whole region. All right, so let's see some of these in action. So let's remember from earlier in this section that we discovered that the integral from 0 to 4 of x squared minus 3x dx is equal to negative 8 over 3. All right, so let's see how we can use that. So I'm just going to put that in a thought bubble. And what we're going to do now is we're going to figure out the integral from 0 to 4 of 5 minus 3x squared plus 9x dx, only using what we've done before this section, or before this point in the section. So for instance, only using this piece of information, and then only using these integral properties, okay? All right, so one thing we can notice is, well, it would be nice to use this, x squared minus 3x. So can we find that anywhere in this expression? And we can, but it's a little bit hidden. Notice if we were to factor out a negative 3 right here, we would get back to this little thought bubble we have. We would get back to x squared minus 3x. Those should be parentheses. So we can eventually make that substitution. Okay, so this is how we're going to do it. So let's distribute our integral sign, because that's one of our properties. When we have a difference, we can distribute our integral sign. So what property is that? By property 4, we'll distribute the integral. Okay, and then what else can we do? If we have a constant times a function according to property 5, we can bring that constant out front. Okay, so now we're ready to evaluate this integral. All right, the first one, this is the integral of, sorry about that, a constant. And we know when we're taking the integral of a constant, right, this is c is 5 in this case, it's going to be 5 times 4 minus 0. So this is going to be 5 times 4 minus 0, c times b minus a. All right, that's what our property says. And then by substitution, this integral right here is negative 8/3. And now we can evaluate that. So we're looking at what? We're looking at 20 minus minus becomes plus, and the 3's cancel. So 20 plus 8 is, of course, 28. All right, so a nice little application of all of those integral properties. Okay, what else can we do? Let's say we have this following question, and this is like number 48 in our textbook. So number 48. Okay, so suppose that the integral from 2 to 8 of f of x dx is equal to, let me find it right here, 7.3. 7.3. All right, and then what else are we given? The integral from 4 to 2 excuse me, number 48, it's 2 to 4 of f of x dx is equal to 5.9. And they want us to find the integral from 4 to 8 of f of x dx. All right, so let's sketch out a picture. Let's see how we're going to approach this problem. We're going, let's see, 2, 4, and an 8. So I'll just kind of mark those numbers. Do you see those limits of integration? We're dealing with 2's and 4's and 8's. 4, 2, 4, 8, okay? So, and we have this function f. And let's write down the information. So we know from 2 to 8, from 2 to 8, this whole region is 7.3. All right, what else are we given? We're given that 2 to 4 is 5.9. And they want us to find 4 to 8. All right, and when we sketch out a picture, it kind of pops out at us, right? We can just take this whole 7.3 and subtract the part, 5.9. Okay, so perhaps we can see that this is just going to be 7.3 minus the 5.9. All right, so 1.4. Alternatively, we know that if we have a point between a closed interval, we can add the integrals, so the integral from 2 to 4 plus the integral from 4 to 8, and that's going to be the same as the entire region from 2 to 8. So we can also approach it just using one of our properties. All right, and of course filling in everything, we know from 4 to 2 it's 5.9. This is what we're trying to find, the 4 to 8. And we know from 2 to 8 it's 7.3. So we're getting the same calculation, that the region under the curve from 4 to 8, that area, same as the integral, is 7.3 minus 5.9. So it's the 1.4. All right, so 2 ways of using our property. Okay, let's see what else we have. And what's coming up next is we're going to be looking at comparison properties. Okay, so we have 3 comparison properties, so let's go ahead and state them. So first of all, if our function is greater than or equal to 0, all right, so our function's above the x-axis for some closed interval, then we know if we're taking the area above the x-axis, it has to be positive. So we can say then that the integral from a to b of f of x dx is also greater than or equal to 0. Okay, so that one's very visual, right? If our function's above the x-axis, then what we know about net areas and everything, the area also has to be positive as well. Okay, let's look at the next one, our next comparison property. So now if we have 2 functions, and f of x is greater than g of x on a closed interval, then the integral from a to b, the integral from a to b of f of x dx, and it's going to be greater than or equal to the integral of the same region of g of x. All right, and then we can just do a quick little proof by picture. So we have a closed interval a to b. We don't really care what the function does outside of a and b, so I'm just going to focus on a to b. So f is greater than or equal to g on that whole interval. Okay, so those are your f, and then, here's g. Maybe they're equal at just 1 point, because that's allowed. And now when we take the integral from a to b of these 2 functions, remember that's area underneath the curve. So we can see that the area under the curve of g will be smaller than the area under the curve of f. All right, so that's this conclusion. All right, so that's what that's saying. Okay, and then finally, if we have a function that's bounded by 2 numbers, little m and big M, for a closed interval. then we have the following. M times b minus a is less than or equal to the integral from a to b of f of x is less than or equal to m times b minus a. Okay, let's unravel that one. Let's do a quick little, again, kind of proof by picture. Let's introduce our two lower and upper limits of f. There's m and m. Okay, so those are the boundaries, and we're saying that f is between those two numbers. Okay, so f is, well, let's get our a and b, because it's only true for a and b. Again, we don't really care about what happens outside of a and b. Okay, so doesn't matter. We just have to be between those two lines. So what we're saying then is that the derivative from a to b of f of x, it's the area of this region, right? That's what the derivative is. We're saying it's between two numbers. And the two numbers are the areas above and below. So for instance, let's look at the area that's formed by the upper limit. That's a rectangle, right? The base is b minus a, and the height is what? M. So that's where this b minus a comes from. That yellow part, I'll highlight. I'm going to get a lot of highlighters, so hopefully it doesn't get too crazy. So that's definitely bigger than the function down below. Okay, so that's why it's the upper bound. All right, and then we have our small rectangle right here, whose height is m, and again, whose base is b minus a. And it's definitely smaller than our yellow region because it was smaller than the function. And again, that area of the rectangle is m times b minus a. And that's your lower limit right there. And again, we can see that the area of that rectangle is less than the area of the region. And again, it's all because that's how we define those first two functions. Okay. So let's see what we're going to do with that. Let's take a look at number 64. And we're going to use that last property to estimate an integral. So we can use property 3 or comparison property 3 to estimate an integral. So let's look at what number 64 is saying. Where's 64? It says use property 8, which is this that we just went over, to estimate the value of the integral. All right, so we're using this method because it's telling us to and because they just want it to estimate. And this is what we're going to estimate. We're going to estimate pi to 2 pi, the integral from pi to 2 pi of x minus 2 sine x dx. Okay, so we're just looking at the interval from pi to 2 pi. All right, so again, we're just interested in pi to 2 pi, from pi to 2 pi. So we're going to have to bound, this is our thought process, we want to bound the function x minus 2 sine x above and below. Another way of thinking of that is we want to find the absolute min and max of that function on the interval, on the closed interval, pi to 2 pi. So we have to go back a chapter. We have to remember, how do we find the absolute min and max? Well, we find the critical values, the critical numbers, excuse me, and we test all the critical numbers and we test the endpoints. Okay, so that's our strategy. We're going to find and test the critical numbers and test the endpoints. So let's find the derivative of our function. That's how we find the critical numbers. So take the derivative of f. So 1 minus 2 cosine of x. This is defined for all values of x. So we're just going to find the zeros. All right, so we subtract 1, divide by negative 2, and the zeros will happen at 1/2. All right, so it's important to remember our interval. It's just pi to 2 pi. So we're just interested in that half rotation. All right, so cosine of x is 1/2. So that means the x value, because cosine is the x value, has to be positive. So that means we're in the fourth quadrant. And the x value, the cosine is 1/2. And that happens at, whoops, when our denominator is 3. So in this case, that will be 5 pi over 3. Okay, so we wanted to get a positive x value whose cosine was 1/2 between pi and 2 pi. So that's how we determined our x. So our critical number is 5 pi over 3. Okay, so now how we're going to test to figure out the absolute min and max, we're going to test the critical number. We're going to test, what are the endpoints? Pi and 2 pi. Okay, of the original function. So f of x was x minus 2 sine x. So we're going to plug those values in. So f of 5 pi over 3 okay, let's see, sine of 5 pi over 3, where is it? So 5 pi over 3, the cosine is 1/2, and the sine, the y value, is negative root 3 over 2, right? Okay, so that means we're looking at 5 pi over 3 minus 2 times negative root 3 over 2. Okay, so negatives cancel, plus plus, 2's cancel, so we're looking at 5 pi over 3 plus root 3. All right, and then let's put that in our calculator. I can't do all that mental math. So that's about 6.97. All right, so there's your critical number. Let's look at your endpoints. Let's test pi. So pi minus 2 sine pi, and sine of pi is 0. So we're just looking at pi, which again is about 3.14. And then finally we'll test the other endpoint, 2 pi. So 2 pi minus 2 sine of 2 pi. Sine of 2 pi is 0, so we're just left with 2 pi, which is about 6.28. All right, so which is the min and which is the absolute min and which one's the absolute max? Smallest is this one, so this is the absolute min on the interval 0 to pi, and this is the biggest, so this is the absolute max. All right, so now that we have those two numbers, we have our function x minus 2 sine of x, and it's going to be bounded below by the absolute minimum. Okay, so it's going to be bounded below by pi, and the absolute maximum was this, 5 pi over 3 plus root 3 on the interval pi to 2 pi. All right, so we were able to use absolute min and max to set up this property. So let's kind of gonna go back to what we're doing and where we're at. So we just found little m and big M. So we were able to set this part up. And now we can take the integral of that original function and we're gonna get an estimate. So let's finish this out. So by that property, essentially what we're doing, and I'll throw in this step if you want. You can also skip right to the theorem as well. But this is essentially that intermediate step. Remember, the integral sign holds over inequalities. That was one of the properties. So that's the intermediate step. And notice the two outside right here, these are constants, right? Pi is a constant, 5 pi over 3 plus root 3 is a constant. So by property of integrals, this is going to be pi times b minus a. Okay? And again, you could have skipped right to what I have in pink because we have this property in pink. It's been given to us. It's been gifted to us for us to use. All right, and then finally this last integrand, well, this is a constant, so we have an integral property that says we can look at the constant times b minus a. That was one of our properties, of integrals, 2 pi over pi. All right, and of course you'd want to, clean it up. So, instead of 2 pi minus pi, you want to write pi. So, that's really pi squared. And then again, this is pi. And so you can, however, there's lots of different ways to express some of these things. So if you wanted to multiply through by that pi, it could look something like this. All right, so now what's happened is using that property, that comparison property, we're able to estimate this integrand, this integral. All right, by finding the min and the max value first.